one. Good. Is what opposite the shape over the shape. That's what change. So guys, you're okay?
Write something so that you can see it.
Yeah. Can you see it?
Yes.
Can you read this?
Yeah.
Okay, good. Okay, so we'll start the. You can see around here by okay.
Sir, I have a small question.
Okay, sure.
Will you send notes or we have to write it?
I'll send you notes. Yeah, no, I have the notes. I mean, they're written in small letters and you have to deal with my handwriting. But
That's fine.
okay, so let's start with. So today's agenda is. So guys, can you see the whole board? You can see the whole board, right? Yeah. Good. So uniform integrability. So you guys know the definition? You know the definition.
Yes.
What do you remember?
I also hate
Think about class of random variables. C is said to be uniformly integrable x in C, expected value of x count x greater than k goes to 0. As k goes to the limit, as k goes to infinity is equal to 0. So all together the random variables are going to 0.
Yes.
And there's this k expectation.
There are some equivalent conditions over there.
Basically, we want to now, the reason we're doing this is we want to come up with a if and only if condition, yes, for L1 convergence. So that's the idea. Now you can see that if I give you x which is in L1, right? Then E of x, indicator x greater than k, this goes to 0 as k goes to infinity. Is this correct?
BCT. Right.
How would you show this?
DCT, sorry, DCT.
Oh, somebody forgot to say. Vaishali, go ahead.
Yeah, yes, sir. DCT.
DCT.
Yes, sir.
Bounded. Huh? DCT.
Dominated convergence theorem.
So what is being dominated here?
Means you can write the function fkx equal to mod x into indicator of mod x greater than k.
Yeah.
Then as k goes to infinity, this function goes to 0. And as mod x greater than k, this is bounded by mod x, and mod x belongs to L1, so we can apply DCT here.
Right. So that's clear, right? So this is bounded by that guy, and this is going to 0 as k goes to infinity. You can sort of hence expected value of this will also go to expected value of 0, which is 0. So that's the difference now. This is always true for everyone random variable, but here we're talking about all of this supremum going to 0. So that need not be true. So a good example of when this may not be true. This is so much more fun. Good example of when this might not be true. Because we never stop like this, right? I never ask questions and then answer.
It's like an oscillating function that is going to just like oscillating function.
We have to say more than that, right? Like we all can oscillate.
The tail will oscillate, but the is going to 0, but tail will be oscillating. So the it's like +1 -1. Area will be in this case 1 by n. It is.
Oh, you're defining, I guess, a one random variable, is that right?
Means yeah.
You define, give me a sequence of random variables, right? So this is a collection of random variables. One random variable in L1 is always uniformly integrable.
Yes. So you want a sequence of random variables for this? It is
Class C, yeah.
Yes.
So that each one is in L1,
but not the supreme.
not the supreme one, yeah.
Now we can take n times characteristic x between 0 and 1 by n.
What's that?
N times characteristic of x between 0 and 1.
What the example that we did last time?
Yeah.
Right, so that example is again this. You can have xn is taking value n with probability 1 by n and 0 with probability 1 minus 1 by n. Right. Right, so now you have xn indicator xn greater than k. Right. So this is fine, but if I look at supremum of this, what can I say about this? It's 1, right? No matter what k I give you, you can always find an n greater than this. So this limit is not equal to 0. Is that clear, guys? Okay. Just turn your cameras on so I can see a very tiny picture, if you can. Malhar, I take it you'll be coming to campus next week? Let's see.
Yeah, I was end of February, March first weekend.
Oh, still good. So this is example of something which is not high.
So you need uniformly bounded sets also to conclude that you can only.
Uniform boundedness
Yes.
of the random variable or of
Yes.
expectation?
The random variables.
No, that we don't need, right? We want to be able to say. No, I think you just say, let me not comment on that right now. But the whole point of this k here is that if it was uniformly bounded, then his expectation will just become 0. So k large enough. That is certainly uniformly integrable over random. But then the bound, if their bound is uniform, that will certainly be much more. Okay. Well, one thing you observe is if class C is uniformly integrable, implies that T of x suit x in C is an. In this sense, you get a uniform bound. They're all L1 bounded uniform. How do you show this?
We can take some k large k, then for that the supremum of x in C like that quantity would be less than infinity.
this is going to 0 as k increases, right? So you'll make it maybe say less than 1.
Yes,
Anything.
anything.
We always find that k 0, right? Okay. And then you're saying that okay, now
Now the other part of the like that is it will be bounded by k.
Yeah.
This and this less equals to.
Yeah, no, I don't want to see. Sorry. Right. This is true for all the vectors. So we get. So this we get. The other way around we don't get. So this does not imply uniform integrability. And you have an example of that, right? The same example we did earlier. That will have this is equal to 1. That's not going to work. Okay. But what would work? It turns out that a small perturbation of this will suffice. Right? If you take that would work. This will ensure that all these x's are uniformly integrated. So if the p moment for p greater than 1 is uniformly bounded, that suffices. Now you could have nitpicked that earlier. You could have taken p equal to 1 and
Do you need a what exactly one P or for all P greater than one?
any one piece.
In one P.
Any one piece.
So you need your function to granular to be in P.
For some p, greater than 1, not everyone. But you can relax this also, by the way, just by the same amount that I'll show you. But nonetheless, this is good enough conditions. And how do we show this? Well, let's just go back to what we want to show. We want to show that this guy is going to become small arbitrary. So each check. The upper bound is by. You know, anything there. These are again easier if you've seen them kind of sort of before. But you know we want to use extra part p, right? That has to come to the picture. So what we can do is we can just x on this set I can bound this by extra part. I guess p minus 1 to the power p minus 1. That will give me an upper bound on this set. Right, because this is greater than equal to 1 on this set, right? Okay. And suppose this was equal to n is infinity. And this is independent of x. So just by choosing my k large enough, so basically as k goes to infinity, this goes to 0. So we have right. So this is sufficient. Other condition could have been okay, I could have just said that okay, suppose my x is less than or equal to y for all x and c, and my p of y is finite, so my y is in L1. Dominant convergence theorem. So if a sequence of random variables is dominated by a random variable which is integrable, then also you get uniform integrability. But the point is, yeah, this is more general. So in some sense, we are extending dominant convergence theorem. In every sense, we are extending. Okay, so is this clear how we proceed here? We'll again go back to the definition and we know what we want to show.
Since y is in L1.
We'll have an upper bound of this, right? So x of course is less than or equal to y, absolute value of x. And indicator x, absolute value of x greater than k is upper bounded by, well, this implies y is greater than k. Okay. Now we are. Now you just put a suit here. And that we know is going to 0. Right? Okay. Okay, so now we developed, we basically defined UI condition, and we've given sufficient conditions for UI uniform integrity. Right? Now we basically state our main theorem, and then the rest of the lecture is about proving that theorem. And then if we have time, then we'll go. So what's the main theorem for today? The main theorem is
Praveen has messaged he is not able to access the online class.
who is
Praveen is
Praveen? Yeah, he was. That's right. Praveen was trying to log in earlier. Just tell me try again. Oh yeah, no, he's waiting, and Shijata was waiting. Sorry. Yeah, good. Thanks for letting me know. I've been waiting for a while, I think. Could we have a recording? Shijata, you've joined, right? Praveen has not joined, but Shijata has. It doesn't have to do with that. Okay, never too late to learn. Okay. Yeah, so okay, so before I state the main theorem, let me just say a few things. So, xn converges to x almost surely. That's same as saying, okay, probability that, okay. So let me just omega it, I guess. So omega is that xn omega is x omega. Greater than, I mean, this would imply it exists, right? That we often is equal to 0 for all epsilon. And we've discussed, and you probably know already. So Praveen, can you hear us now? It's trying to connect. Anyway, you can see the video. And we know that, okay, xn converges to x in probability. We know the definition, right? And you know how to show that almost sure convergence implies convergence in probability. But you know it does. You may not remember the proof.
So what about the pointers?
Yes, we'll discuss that. We'll discuss that in some detail. Okay, sorry. I'll just keep it above my mouth. I usually breathe from my mouth, so those doesn't matter so much. So the risk is under control. Probabilities are very much under control. Okay. I'm actually saying it to the camera. Somebody reports me later. Okay.
So for the converse, do you need the uniform integrity?
No.
We don't need
Right,
that.
something like that. Okay. So you're saying vendors almost showed, vendors conversion probability imply almost showed conversions. I mean, what additional conditions do we need on this?
Minimum.
I don't know if there's a nice way to say that. You can put some more conditions. I mean, you need more conditions, but yeah. Don't know if there's a simple way of saying that. I mean, of course, we can differentiate between the two. But what extra thing is sufficient to ensure? I mean, you can kind of go back to Borel-Cantelli and those kinds of things. So we'll see some of that here right now. That will explain the idea of, what more you need. So let's see. So let me just see myself. Okay, so this is of course same as saying, okay, probability that length soup of the event this is equal to 0, right? That's what this means. Infinitely often just means length soup. And we've already done that this is less than equal to. So I'll just use the well-known result. You can do the first principle also. Right, lim soup inside, lim soup outside. This is called, I mean, we've done this, but more generally, this is called reverse Virtuous lemma. So we'll use it again one more time. And this, of course, is the identity, right? Not negative terms. So hence, you get that. For any epsilon, almost sure convergence implies that this limit is going to be 0. It will exist in it. So convergence probability is implied. Now, so some things are there. So let's do some examples first of all. Let's do an example of, so let's propose this in two different ways. First, I'll show you an example of something which converges in probability but does not converge almost surely. Nowhere does it converge almost surely. And second, we'll say that even if something sequence is converging in probability, I can extract a subsequence which converges almost surely. Right? So that gives us more insight into what we want. So let's do this. So I create this space omega is equal to this. I just like to do this example. It just clarifies things a lot. There are simpler examples to make this point, but this example is a nice one. So we have omega f and the big measure. F can be the big sigma delta or one sigma delta. Now, so let's think of this space as this is your 0, this is your half, just sort of points on the circumference. Take it 0 1 here. Now I'm going to keep this guy as, let me just call it C1 as equal to 0. Have you seen this example before? Where you have convergence in probability, but not almost sure convergence.
Not this construct.
Hmm?
Not this construct.
Not because so let's construct now. C2 is equal to C1 plus 1 by 2. C3 is equal to C2 plus 1 by 3. Right? So C2 is 1 by 2, C3 is 5 by 6. Cn is equal to Cn minus 1 plus 1 by n. If Cn plus 1 by n, Cn minus 1 plus n is less than 1, doesn't matter. Cn is equal to Cn minus 1.
You are trying to define partial sum of the probabilities.
But we are also taking more.
No, I'm just defining these
Yeah,
gaps.
this is the partial sum for the 1 by n series, right?
Yeah, for 1 by n series. But I'm going round and round basically. So I'm kind of taking modulo 1.
Yes.
So because it's modulo 1, this sum is going to go around infinite amount of times. The circle. Right. I mean, this is just very geometric. Would you believe?
Yes. The point CNS will be dense or it will be like.
No, they'll be countable, right? They countable.
I said it will be dense in the circle.
No, but if they're countable, how will they be dense? Oh, you mean dense? Yeah, of course, yeah. Sorry. Are they dense? Are they dense? I guess they must.
Because the rotation is changing.
They must be. Because you're getting arbitrarily smaller, right? As you go around.
Yes, but.
So to every point you get arbitrarily close. Right? If I'm going to go around every point infinitely many times, and every time I go, I become smaller.
Yes.
So I have a point which is arbitrarily close.
Like we
That's a
can.
good point.
It will like kind of like dense in the fold region, like each time when it is like, okay, then that's picking the one and then only adding that 1 by n.
Yeah.
That will be very much smaller than. So
That's right.
it's like dense in the fold 0 region.
No, it'll be dense everywhere. Because every point is going to be covered by this interval, and it'll be covered by this interval infinitely often.
Like that.
So every time, and then you're becoming smaller.
I didn't run this.
No, so take any point of the circle.
So basically, you were trying to map on 0 1 interval. This and you were doing one. Yes.
No, but that's a good question. So I take this point. Now, do you agree that I'm going to have this interval? So interval I'm going to define as Cn minus 1 and Cn, and then in the natural sort of way. That interval is going to cross this infinitely often, right? Because in the intervals are all contiguous. So every time I go around, they are going to go around this. Every time I go in the circle, I'm going to go infinite amount, right? Every time I go around, I'm going to cover this point, right? And every time I cover this point, my interval is smaller and smaller. So I'm getting arbitrarily close to this point.
The step also reduces every time.
Yeah. Because the step reduces, so I can find a point arbitrarily close. That's a good point. Okay. So yeah. So now I can define random variable xn to be equal to 1. Let me say it's like this. I'm not going to worry about these issues a little bit. But, if Cn is equal to 1, or zero to
But you already defined Cn to be between 0 and 1, right? Oh, I see. Yeah.
right.
Cn would always be between 0 and 1, right?
Yeah, Cn will always be less than. That's true. Yeah, so this is so I'm not being careful about definition of 0 and 1. That's why the same point 0. But those are nuances that are not so important. Right? So you can
Isn't like first condition should be like Cn minus 1 less than
So Daksh, what do you say?
like first condition, isn't it like Cn minus 1 should be less than Cn?
Cn minus 1 is like Cn? No.
Is less than Cn.
Oh, yeah.
Something.
What did I say? What do you mean
It should
here?
be Cn less than,
Yeah.
if it's Cn minus 1 less than Cn, then it should be the first one. If
Wait,
it's
it just automatically.
otherwise the second one.
No, his point is valid that Cn minus 1 less than Cn.
Cn.
Less than equal. No, that's a good point, yeah. And if Cn minus 1 plus 1 by n is greater than 1, then you get this from then you go up to 1 and then after that. Right. That's okay, right? Right. Okay. Okay, now with this definition of xn, so what's the probability that xn is greater than 0?
One by n.
One by n.
1 by n, right? So what can you say about xn? The sequence xn.
Yeah, it goes to 0.
So yeah, xn converges to 0 in probability.
Yeah, in probability it goes to 0.
Now, can I say that yeah, it should be 0 as well. Okay. So what can I say about this? Xn minus 0 greater than epsilon. Insert the option.
It doesn't have a limit.
Sorry, what do you think, Malal?
It doesn't have a limit. I think.
It doesn't have a. Right.
So if you choose epsilon equals to half also, you will get.
This is going to be equal to 1 actually, right?
Yeah.
Right. Yeah.
For any epsilon less than 1, with xn on any point on the circle, this is going to become 1 infinity. So yes, on all of those, so no point you have almost sure, on no point you have convergence, pointwise convergence. While you have convergence in probability. For n large enough, the set of points where xn is not equal to 0 is small, and that's Kishan. So this is kind of an instructive example, right? That draws home the picture. I mean, I could have also just said, okay.
It has the subsequence also.
What's that?
It has a subsequence, but that.
Yeah.
It has it.
It has subsequence.
But to get a sequence is a bit difficult.
Yeah, I mean, just ignore the points where you're crossing,
Yes,
then that is always conveying to 0.
like we have to make sure that the step size reduces at exactly 1 point.
Step size reduces at exactly 1 point. What do you mean by that?
Like
So data, yeah, please go ahead.
like something of the form like 0 to 1 by n, or there must be some point or some neighborhood where the step size is getting long. It must not be like the whole interval.
So I'm still not understanding. The whole interval what?
I mean, the value 1 is migrating over the interval, and the set,
Yeah. We log in here, right?
everything that happens.
Actually, you don't need, I think
Shinata, at what point did you realize that you were not the right tool?
No, I knew started the class.
Okay.
I asked.
So you can take a relational rotation that will also say
You can take out?
irrational rotation theta rotation by theta.
Yeah.
That will also give you the same answer. You don't need to create this.
Yeah. Oh, that's true. That's true. Yeah, you can just kind of rotate by irrational angles.
Yes, that will be
Sure.
that will give you.
Sure. There are many ways of doing this. Yeah. So what's your point again?
Yeah, like I was saying that the inconsistency here is because the value 1 is migrating throughout the interval infinity.
Yeah, that's right. That's right.
So to stop it, we must pick a subsequence such that it happens only in a neighborhood and the set size goes to 0. I mean the measure goes to 0.
Yeah, I mean, so suppose I'm looking at this point outcome, right? I just want to miss out those xn's which are crossing this. So any subsequence which misses them out is going to be on this point, it's going to be okay. But now your point is that you want to come up with a subsequence which everywhere is converging.
Yeah.
Right. Right.
So in that case, we have to use that the fact that it will be dense in 0, 1.
Oh, yeah, that's okay. So I guess the question is now, can one imagine a subsequence which is converging everywhere? Right. So that's a question that's being discussed.
What if we pick a point
Yeah.
and then we consider only those intervals which intersect this point? So this point omega that we pick, it will be 1.
Yeah. Yeah.
Then the only intervals which we are considering are those which are close to each other. So then it's not moving around the circle.
Yeah. Yeah. That's a thing. That's a move around. So you're somehow saying that. No, I agree with you. It's an interesting question that.
But that will also happen if the set of points is dense in 0, 1. So that for every value of n large enough, you are going to get an interval in which the point x is contained.
Yeah. But that is true. But what's your point in this?
What Malad is saying is we are going to take the interval Cn minus 1 to Cn in which x is contained and construct the subsequent. So to make sure that it happens, we need that the sequence Cn is dense in 0, 1. Otherwise, maybe after some large n there is no such interval.
Yeah. So that of course we argue that Cn is dense. But the question now is, can you construct a subsequence in an obvious sort of way, which is going to converge everywhere, on which x and I omega is going to 0 for all omega.
Yeah. So what I was saying was you pick a point on the circle.
Yeah.
Let's say x1, I don't know what to call it. Omega.
Okay, whatever, omega 1.
Omega 1, and then you pick only those for which x and I of omega 1 is 1.
Yeah. So we get a subsequence, right?
Yeah, we get a subsequence.
So then
all the intervals, they are becoming smaller and they all contain this point omega 1.
yeah.
So they're not moving around the circle, they are just staying close to this one, this point omega 1.
So that is true, but that doesn't give us a subsequence along which your point is that all the other points is
Yeah,
going
all
to
the
be-
other points will be going to 0.
Okay. So along that subsequence, that's a good point, yeah.
It's almost everywhere.
Yeah. It's almost everywhere, sure. So on that particular point, it will not, but everywhere else it would be, yeah. So that's true. So that's a good point. That's a good argument, yeah. Good. So any such subsequence would work, I guess. You take any point here and just look at the subsequence which crosses it. That's going to be 0 everywhere else. Thanks. Okay. So I guess that's almost everywhere.
Yeah, not everywhere.
That's
the confusion of the theory.
maybe everywhere will not really not exist.
It's for this example, it's not.
Yeah. No, for this example, yeah. Because I guess I give you a subsequence, arbitrary subsequence, so I have to look at subsets. You know, if I give you, if suppose I say that this sequence is everywhere, then ni corresponds to some interval, right? For each ni I get some interval. So the point then is, so can you have
I might be wrong if you can break the function itself. If Cn will be 0, if it will be 0 when Cn equals to 1 exactly. And if you look at around the point 0, you have to modify the function.
yeah, I mean that of course it will modify the function.
Because I am trying to say that in the you have 3 steps functions, right?
Yeah.
So if you just take another function, for which for strictly less than 1, it will take the value 1, and if for some xn it is Cn equals to 1, then the value will be 0 here. Then you can try to take the Mallar's argument over the point 0.
You're saying define one point in such a manner that you always, whenever you come across it, they are always zeros, right?
And the rest
And
is
then,
very
then
strict.
in any case, things are shrinking. Yeah. Okay, so that could be one argument. Okay, so let's hold that. But let's see, even with the current constructor, if there's something that makes sense. Anyway, let me spend a little bit of time on this. Saying that both construct a subsequence of these pictures in such a way that no point is covered infinitely. That's what I'm saying, right? I'm just covering this picture here, something smaller, so on and so forth, in such a manner that no point is being covered by this thing infinitely.
That's not possible, right? Because it's the argument that you gave in the first, that is of the density.
Right. I mean, I'm saying that each point eventually is going, no, because subsequence can be different, right? I can, but the overall area of the subsequence can be finite. I can always do that, right? Suppose I look, yeah, maybe that's the way to do it. Suppose I choose my area was 1 upon n right now.
Yes.
Suppose I choose my ni, so it's n squared.
Yes.
And then for even smaller than that, then I get something which is small, right? I mean, I can choose it in such a manner that this is less than 1. So then the total area that I'm covering is less than 1. So some points are not being chosen, but that doesn't mean that all the points are not being chosen, right? But I can of course make this now, I mean, arbitrarily kind of small, the area that I'm covering. I still have a subsequence, but I can't kind of make it. It's a nice problem, yeah. So let's think about this maybe offline. In a natural sort of way, can one kind of come up with a, not by cleverly, having the people or something like that. Okay. So let's do offline. Okay, so this is one example. So now I guess you have to tell me that suppose xn converges to x in probability. How do I get a subsequence so that along the subsequence, let's say ni x and I x almost should. Yeah, I would imagine that above part should be possible. You should be able to construct a subsequence so that after a while, no point is covered in failure. No point is covered in failure.
So for the circle example,
Huh?
yeah, for this circle one, if we take, instead of just picking one point omega 1
Yeah,
and fixing it, we can take a sequence of point omega 1, omega 2, omega 3, and so on.
okay.
Then you take a bunch of intervals intersecting omega 1, followed by a bunch of intervals intersecting omega 2,
Mhm.
then bunch of intervals intersecting omega 3, and so on,
Mhm.
such that the intervals which intersect omega I, they don't intersect any previous omega.
Mhm.
So then for any omega I, once you pick any omega I,
Mhm.
once you've started selecting intervals intersecting omega I plus 1 and so on, then that will never be 1 again.
Mhm.
So every point will be eventually be 0.
Okay, I see. That's a thought.
But except for the limit point, they might, if the sequence tends to a limit, then the limit point may still end up being 1.
Right.
Yeah.
Well, okay, so that sounds like a line of thinking, but you can complete the argument offline and we can take it up next time.
Yeah.
So let's talk about this right now.
So can you just arbitrarily large integers in the probability xn minus x greater than 1 by n is less than 1 by n?
So let's say you're saying
xn
extend you want, extend here.
xn minus x greater than 1 by n is less than 1 by n.
It's less than 1 by.
Otherwise, the distribution functions. This is true for arbitrarily large cells.
I mean, but
Yeah, to take a convergence is.
yeah, so with that, so that's why you maybe want to get 1 by x squared.
Yes.
Yeah. So that part is fine. But can one do this for every n?
No, so n1, n2,
Yeah, that's fine. That's fine. So let's do this at let's call this ni. Let's call it 1 by I, and let's call this I squared.
It's almost like solutions.
This I can always do, right? Because I'm given conversion probabilities. I'm given that okay.
Otherwise, the distribution functions of xn would not convert.
So and for all epsilon. So when I can do this sequentially. So after I've chosen ni minus 1, I'll choose ni so that my epsilon is equal to 1 upon I. And I'll choose ni to be bigger than ni. So that's all this. And I'll just go forward until this becomes equal to 1 upon I squared. And then I can repeat that. This can always be done. So now what do I get from here?
So probability that limitation yes, so the sequence will always form the probability at least one. So we can make this a slightly lesser constant. So the assumption is less than 1.
Okay.
And then you get that by union bound, the probability that the probability that at least one of this is false is less than 1. And probability that it does not converge is less than 1, and by 0, 1 log it has to be exactly 1.
Let me just tell you what we want to show.
Okay, so this x and I will go to x almost 0.
Yeah. So you're saying that somehow we make this also small.
If you can make the sum of these probabilities less than 1,
Yeah.
the probability that these convergence scales
Mhm.
is less than the summation of this 1 by I square.
Oh, you're saying some of these probabilities?
Yes.
Oh, I see. So that of course, suppose, so let's look at the sum of these probabilities as we have it right now. What can we say about that?
So I say,
I know.
let's make. Okay. So here instead of 1 by I square,
Yeah.
you would say 1 by 100 I square.
So you can make this as small as you want. Okay.
Yes. So this is less than 1.
Yeah.
But this also upper bounds the probability that this fails to converge.
Mhm.
Right. And the probability that it converges is either 0 or 1. So it has to be 1. And the probability does not converge has to be 0.
So this is just for, I see, so you're looking at summation of these guys. I see. So your point is that let's make this, for example, equal to epsilon.
And 1 by 100 I square. So
1 by 100. This whole thing you wanted to make.
yes, this whole thing I can make less than 1 by 100.
You can make it epsilon by 2.
Okay. Epsilon, that's fine. So I make it arbitrarily small. And now your point is.
So now this is the upper bound of the probability that this x and I does not converge to x.
This is the upper bound of the x, right? I see. So your point is because it's epsilon and epsilon is arbitrary.
No. So once you fix epsilon, this ni's are fixed.
Can't use Boolean control now.
But the issue here is that these ni's can depend on epsilon. But I am claiming they don't because you know the probability that it fails to converge is either 0 or 1. And if you make the upper bound strictly less than 1, that means that's
So how do we know that states converge is either 0 or 1? We're not going to use that right now, right?
So can't use Boolean control now.
Yeah, no, I was hoping that, so Shano, you're right, that's the plan. I mean, that would be the most straightforward way of doing it. If we just were here, then essentially we're done, right? Okay.
Yes, sir.
And that's what I'm saying. Because now Borel theory tells you that, okay, probability that x and I minus x greater than 1 by I
Infinitely often equal to 0.
is equal to 0. And that's right?
Yes, sir.
So on every set omega, you're less than 1 by I. I mean, that basically tells you, okay, probability that x and I minus x is less than equal to 1 by I
Eventually equal to 1.
is equal to 1. Right. And that corresponds to, and that means that all the omegas are there. Yeah, so that seems much more messier. We don't want to grab that. So it's called Log 0 now. That's big hammer. Okay, chalo, so we got this out of the way. That and I guess we can also now argue that okay, suppose xn converges to x in probability, and suppose xn is less than or equal to y for all n, and u of y is less than infinity, right? So we're trying to generalize the way to argue that u of xn, no, sorry, u of xn converges to e of x. Right?
This is just dominated convergence.
No, I mean now the only difference is this converting in probability.
Stronger.
Yeah, so it's
There will be a subsequence.
বুক করা হয়নি
where Chandra want to complete the argument?
There will
আমাদের নয়
Going, you were saying
there is a subsequence is actually converges pointwise almost surely to x.
Yeah.
And by automated converges to the expectation of that subsequence will converge to x.
so that's right, but that's still across subsequence, right? We want the whole sequence to converge.
So you can say expectation xl from the Cauchy sequence
I see.
because their difference is so take
Cauchy sequence will mean all the points eventually become arbitrary close.
and then subsequence. So first we can show that expectation xl from the Cauchy sequence.
Yeah.
Because take larger of xi xj, then expectation of xi xj equals to epsilon into epsilon plus something small because with probability at least 1 minus 1 by n, they are within epsilon of each other plus and remaining is at most 1 by n. So the expectation of xi minus xj for larger than pi will be less than epsilon for every arbitrary epsilon.
So no, hold on. So all you have right now is the subsequence you have this, right?
Yes, and now if p of x is a Cauchy sequence, then
No, so this is all we have right now.
yes.
Somehow you're saying that we get a Cauchy sequence from here.
No, e of x in itself is a Cauchy sequence.
Yeah, why is that the case?
We still haven't used the mode x is even counted by one. Mode x is counted by.
No, we have, right? Now here, so we use, we got a subsequence which is almost short convergent. And that was also dominated. So by dominated convergence, we got this.
Okay.
So this we got. But now he's claiming that we've got a Cauchy sequence of this. So this is just a sequence of numbers now. But along one subsequent sequence. So I'm not saying. So I just want you to remind you of this result that we say that sequence of numbers converges if you can complete this.
For any epsilon greater than.
No,
For every subsequence of it converges.
No. If every subsequence contains a further subsequence which converges. So that's the nice thing that if
You are going to subsequence of the subsequences.
yeah, so the point, so this is a nice definition that okay, so of course if a sequence converges, if a sequence converges, every subsequence converges. But it's more general that if every subsequence has a further subsequence which converges to the same value, then the sequence converges to the same value. Because you have a contradiction otherwise.
Yeah.
So you are trying to make the subsequence that is chosen some elements from the xni and some elements that is not in xni.
No. You just give me arbitrary subsequence, right? That will still continue to converge in probability.
Yes.
And I'll be able to extract a subsequence from that, which converges almost surely. And on that I'll get this. So along every subsequence, there will further be a subsequence which will get this. So hence these numbers must be converged to real. So that's clear, right?
I see that which you are taking. Firstly, you take a sequence. You got a NI, XNI. You are now taking the remaining elements, if there is any subsequence that is not taken in XNI. And you are again applying the same logic, and you are taking a subsequence every time.
Yeah, but the point is, you give me arbitrary subsequence. That should further contain a subsequence which is converging to the same limit. Then the sequence is converged. So any arbitrary sequence you give me is going to converge in probability, and I can extract from it further subsequence which is converging almost surely. So along that I get this. So every subsequence has a further subsequence where this is true. So this whole sequence has to converge. Because if the sequence is not converging, then you can always come in when there will be some epsilon and you're always away from epsilon by infinity often. So then you have a subsequence which will not contain a subsequence convergence. Okay. Okay, so now I think we're ready to state our theorem. Yeah. So theorem is, suppose I have a sequence xn and x in L1, right? Then xn converges to x in L1 if and only if xn converges to x in probability and sequence xn is okay, so that's a big term that we have. Guys, I'm not seeing your cameras on. Right?
Only you have shown the only
What's that?
xn goes to x in L1 implies that xn is uniformly.
That we've not shown yet.
Yeah,
We haven't shown that either yet. We've not shown anything so far. We just discussed the relationship between almost show convergence and convergence probability. And then before that, we were just trying to understand uniform integrability. But what's nice is that's very satisfying that you get if and only if relationship.
Yes.
Okay, so let's go in the if direction. So we assume one and two. And we show that this implies L1 convergence. Right? Okay. Now we need to show, so we basically need to show that E of xn minus x is less than epsilon. For all epsilon, there exists n epsilons rather than. So you give me an epsilon, I can give you an n epsilon, so this is properties. That's what I need to show. Right. Okay. Now what I will do, I define this cap function is equal to, so this is kx, so it's equal to k if x is greater than equal to k, it's equal to x if x is absolute value of x is less than k, it's equal to minus k. Then this equals and why I'm going to define this function is it's a bounded function. So I can use bounded convergence here. Okay. Now I'm given uniform integrability and convergence and probability, and I want to show L1 convergence, right? So what I'll do is I'll simply write this as xn minus phi k xn plus xn minus pkx plus
First part is less than epsilon from the right?
First part is an epsilon by uniform integrability. I'll just use my K lambda. Same with this guy. Just use my K lambda. So both of these are less than epsilon by 3. Second part.
Bounded
Bounded.
Yeah.
That's bounded. So I just so for these two, I mean, I want to make this guy less than epsilon by 3 and this guy less than epsilon by 3. And I get that by choosing my K lambda. For this guy, I just, I've chosen my K already now. With that K, I choose my N large enough. It's that simple. And we needed convergence and probability for this two. Okay, we needed uniform integrability for this two. This just falls for integrability. Okay, now we go to the other directions. Now we are given now that E of xn minus x goes to 0. Right? Now from here it's clear that xn converges with probability. Is that part is clear? This Markov's inequality. Markov is solution, right? So what we need to basically now show is that we have a UI sequence. Okay. So we need to show that this guy is made a really small, like K now. Okay. That's what we need to show that as my for at least supremo mode. So I need supremo mode. That's what I need to show basically. So okay, so tell me with contradiction. I mean, one could always consider that proof. I go with the proof which I read from the book. But
Some means that will be, I think, easier. If it is not going, then somehow we can show that xn, E of xn I minus xn not going to 0.
so you're saying, suppose I don't have uniform integrability, then I won't have this.
That, yeah, for subsequence, that will be greater than, that will not converge to 0. So means you can choose that is I have some epsilon always. You can choose a main right, and therefore that part somehow.
So suppose I don't have uniform integrability. Now what does that give me?
There will be a sequence of x and I for which this is greater than some epsilon for all epsilon.
Yeah. Okay.
And you
That would
have
be that straightforward. Yeah, I agree with you that so you get a subsequence like that. And but you get for any K that you will exploit that right also. I mean, so the question you're asking is if I give you a sequence which is not uniformly integrable, what does that mean?
yes.
First one cannot be bounded by epsilon. First term out of 3 cannot be bounded by epsilon by 3, right?
Sorry. First term can be?
So this is you're asking what goes wrong if UI is not there, is it?
Yeah.
So I think it's that the first expectation, you have 3 expectation terms. The first one cannot be bounded by epsilon by 3.
First term cannot be bounded.
Because you don't have a because you want to choose n after you choose k, but you're trying to bound xn minus phi k of xn.
So, Malhar, I think somewhere there is a voice quality issue. But let's just understand. So what we have is this.
Not going to 0.
I guess so. This is not going to 0, right? So this is not going to 0 because we have as k goes to 0. That's all we have. So now what are you saying? What does this imply?
So you can choose any epsilon less, any epsilon
Yeah.
small enough.
Right.
Then there will be this peak in I sequence,
Yeah.
for which the sequence will be always greater than epsilon, the optimum.
Right. I mean, that's you want to say that show that this is not going to zero, meaning it's above some epsilon infinity offer.
Yes.
Right. That's
Infinity, yeah, that I mean.
So
And
you can
corresponding to that x and I,
Yeah.
you can just put it there and you can somehow, I guess it, you can somehow argue that the expression will not going to.
so you
So
can-
it's one of those things that you should probably just spend time
Yes.
offline and see if you get the whole argument to work. It's not clear. And there are a lot of kind of things which we covered up.
So just like we did in the if portion,
Yeah.
we can have upper bound expectation of absolute value of xn minus 5k of xn
Yeah.
as less than equal to mod of xn minus x
Mm-hmm.
plus mod of 5k xn minus 5kx
Mm-hmm.
plus mod of 5kx minus x.
Mm-hmm.
Now you know assuming expectation xn minus x goes to infinity,
Yeah.
the first term goes to 0.
Assuming x n minus x goes
The expectation of absolute value of xn minus x
to infinity.
0, sorry, 0. As n goes to infinity. The first term goes to 0.
So cool thing would be that you guys do this offline, write a 2-pager and either mail to me or to all of us. Yeah. So just do face. Let's see if you can come with something more again. So I don't spend time thinking about these things, so I can't immediately tell you, okay, there are 5 different results like this. But let me just tell you one way which I do see. This is from Dave Williams. And then the idea is, well, that also is fairly intricate. It's not so straightforward. That's why it seems that even whatever you try will not be so straightforward. So we want to show this. We want to control this thing, right? We want to show that this is for k large enough. This is less than epsilon for all, not for any n, but for all n.
That is yes.
Right. But the thing is, for finitely many n as such, there's no problem. If I want to show that this is less than epsilon, because for each random variable, I can choose k large enough to be less than epsilon. So for finitely many n things are not going to be an issue. The issue only happens when I go to, because my n it has to be 2 for all the n. So there I observe that I can upper bound this by e of. So I'll give you the proof from David Williams, and you'll see it's not trivial. And then you can think of alternative proof. E of x xn greater than k plus this of course upper bound is there. So I'm exploiting the fact that xn is getting close to x. Okay, that's one fact I'm exploiting. Other fact I'm exploiting is that on this set, I can make this set as real as I want. And that allows me to make this term as small as I want. Right? You ask me, how does this become small? So, as such, the variable n is a problem, but at least I can show that this guy can become arbitrarily small. Because x is in L1, right? And then this difference also I know is going to 0. So it's okay. So what are we saying? So first I have to show you that I can make this guy arbitrarily small. And that of course I know. So for this I'm going to use a result. It's a nice result. Okay, so the result is as follows that so given that x is in, so this is a side basically. So x is in L1.
The tail of the
For all epsilon greater than 0. So this is slightly more general result. It's probably useful in other settings too. So you give me an epsilon basically. There exists a delta greater than 0 such that E of x indicator f is less than epsilon whenever P of f is less than delta.
If is
Any set. So any f is just a broad for f in sigma set. So this is a kind of nice result that not just the tail event, because the tail event was, if it was x, it would have been fine, but I have a tail event for xn. It's saying for any f which has small probability, this must be small. And this is, the proof is, it's a little remarkable, it's little non-obvious. So this is a proof by combination. And you see, so suppose this is not true. That means there exists epsilon 0. So even if I take fn to, no matter how small I take fn to be, I get E of x indicator fn greater than epsilon 0. And I can take E of fn to be less than or equal to 2 to the power minus n. It's up to me, I can just take it when it is. But 2 to the power minus n sum, so that's what I do. So if that's not true, then this okay. Okay. Now this tells me that probability that Fn infinitely often is equal to 0. This term here, this word can tell you. Now so I need to use reverse Pareto's lemma in this analogy. That basically says that suppose I have Cn. Cn is less than y. Then I have I want to say this E of lim sup of Zn is greater than equal to lim sup of E of Cn. So this is reverse for 2. So expected value of lim sup of Zn is greater than lim sup of expected value of Zn. But to prove this, I need some regularity condition like this. Because once I plug in this regularity condition, then I can just use y minus z of n and apply for 2 to get this. Okay. So this is okay for us because our x indicator xn is less than equal to expected x. I mean, in this, of course, I need that y is infinity, right? So I can apply reverse Pareto's in that setting. Okay. So then I guess that E of lim sup of x I of fn is greater than equal to lim sup of E of x indicator fn is greater than equal to epsilon 0. And this is just this is 0, right? Because this is exactly This is exactly the element that we showed, this guy here. So it's just E of x into the element that I of x into P of. And this indicator is 0 almost surely. So this whole thing is 0 almost surely. So this is 0. So that gives you the contradiction. So now with this result with us. So yeah, I mean, I would encourage you to try for a simpler proof. There probably is. You can even with this classical stuff, so you have to read around also on it. I just haven't done that.
That was more very strong theorems.
Huh?
In this proof, we have used very strong theorems.
Yeah. Yeah. And that's why I don't think it'll be that different. Whatever it says. So now with this guy, I can choose my k large enough now. See, I want to bound this, but for all n, not just for any n, x and get in k for all n. So I use this fact as follows. I will use the fact that when I have p of xn minus x is going to 0, that implies that e of xn so n is less than xn. Right? Because e of absolute value of xn is e of absolute value of x is something which I can control. First few terms don't matter, they are always going to be finite. So I get that. So I have this property. Now I can use Markov property that p of xn greater than k is equal to sup n p of xn upon k. Right? So I can make this set to be, if you give me any epsilon that you like, there'll be a corresponding delta, and I'll choose my k so this thing is less than delta. So this is all we're going to be. This set will always have probability less than delta. So that will allow me to bound this result. So I bounded this result here. This becomes small eventually. I still have to worry about this quantity for the, because this will become less than, so you've given me epsilon, so I'll make this less than epsilon by 2. Okay, and I'll make this guy also less than epsilon by 2 by choosing my k last time. But then I still have to, and this is epsilon by 2 for all n greater than or equal to some n epsilon. So I still have to worry about what happens till that n epsilon, but those are finitely many terms, so I'll choose my k again large enough, so that this term is less than epsilon for all those guys as well. So all the way n to n epsilon. So it's an intricate argument, it's not that straightforward. You have to get the sequencing right.
Dealing with finite even elements is not an issue.
What's that?
Dealing with finite.
Yeah, that's not an issue. So I have to choose my k. Well, so let's see. So first you give me an epsilon, then I give you an n epsilon. Then I have to choose my k so that all these guys up to n epsilon are less than epsilon by 2. Okay, so I've chosen a k like that already. And then I further choose my k so that this is also less than epsilon by 2 for all n, which I can do from this property. With that I'm done. So now I've shown that okay, I'm going to be less than equal to. So yeah, so best of luck. Nice to see if you can go with a fundamentally different proof. Okay, so we still have 5 minutes. Let me just say one small thing then. But you want to stop like that? I'll just say one very quick thing. It's something you know already. So just so that I want to complete some stuff. You know that we touched upon this thing. So we know, we define this measure mu a is equal to integral f d mu over set a. R, yeah, was public space mu f. Not a measure space, not public space. I have a function f which is measurable with respect to f, and it's non-negative. So then we argue that this is a new measure, right? And you assume that, okay, let's assume for now that, okay, d mu. So it's a finite measure. Now we want to argue that, okay, integral h d nu is equal to some other, so let's say another function. Let's take h to be another function which is m f non-negative. So what is that equal to?
HF.
Yeah, it's equal to HF d. You've seen this before, have you seen this? No. But are you seen this?
Yeah, I've seen this. I have seen this.
You've seen this. Okay. How do we show this? Yeah, so standard machinery.
Standard.
So if you've not seen the standard machinery, if you want to be reminded of it, you observe that this is true when h is an integer function. So h is any model function here, right? But it's I guess any measurable function. So if h is any, yeah, I guess that's true. It's just a measurable function. So if h is an integer function, then this is true.
The proof for it.
By definition, that's how we defined our measure new a was this for all a's. Then simple function.
Simple function, then you have to pass to the.
That's right. So then so for every simple function also it's true because it's true for indicators. Now any function, non-negative function can be approximated from below by simple functions. For simple function, this is true. So let this be hn, this be hn. Hn is increasing to h. So by monotone convergence theorem, this is
Real FTP.
was that? Yeah. Yeah, I did tell you a sigma finite product. I guess we just need a monotone convergence theorem to work this. So this is hn is increasing to h, and that tells that this guy is going to increase to integral h d mu, and this guy is going to increase to, everything is non-negative, right? So you can apply monotone convergence on h d. So they are equal to each other. This guy increases to this guy, this guy increases to this guy, so they two have to be equal. Okay, so good. So what we do next is, so I'll just mention that. So this basically, f is called the density function of nu with respect to mu. So let me just take this up next time. I'll mention what the Nicodine theorem is. This was my plan.
You will define derivative also, right? Derivative.
Yeah, that's what the density function is. The derivative. Then I guess I'll do some kind of LP space is complete and L2 space. I'll talk about its projections. You've done all this, I guess, but maybe not in the probability context. Is that right? Okay. So LP space, you don't know it's going to, I mean, you don't know the proof of that, right? Okay, so those things we'll do next time. So we'll do L2 spaces, LP space is complete, L2 space as projections. And then we'll move, then I'll just state Fubini's theorem. It's a lot of kind of obvious technicalities, so I will not prove it. You can read up on it. I think David will do a good job. And then we'll talk about conditional expectations. So I presume you've seen conditional expectations, but it's probably good to revise it again, right? Because it's kind of cool stuff. There's all nice things there. So we'll do conditional expectations properly, and then we'll move to martingale after that. So that's the agenda for now. Martingale will probably take 3-4 lectures, and then we'll move on to Brownian motion. And then we'll do the articulation. I think that's more or less been enough. If we have time, we'll do some more things after that. Okay, any questions? So yeah, I think there are a bunch of interesting ideas. If we can do something online, that'd be nice. Okay, I'm going to stop the recording now. Yeah, how do I stop the recording here? Okay.